Yeah, all right. So last time we were making our way through talking about policy gradients, talking through a lot of the points that, they do technically and mathematically work fairly well, but there's still lots of places to improve. And where we were getting to is being able to estimate the policy gradient a bit better. So here we started making this connection back to baselines here, where there's this idea that at least if we can figure out how to reduce the amount of variance in the policy gradient estimate, then there should be some improvement in the way the policy learns. Normally, this results in some sample efficiency. It should also result in some ability to find a higher value policy as well. But what we're going to do is talk a little bit more about the types of baselines to use here. We went over this a little quick in the last 30 seconds of the last class, so I'll go through it a bit slower here. So we talked about being able to use this baseline, which is just rolling out a bunch of trajectories, take the average and basically subtract that. And that's basically a good place to start. But from this, it's also extremely noisy. So if we could have something that's a much better estimator for the policy's current performance, should give us a lower variance estimate of the policy gradient. But this means we're just going to introduce this one concept, which is reward to go. This basically means if the policy starts here, at some state, and then from there, the agent follows its policy for a little while, it's basically, the sum of all those rewards that it gets into its future. So not stuff that it's collected or stuff behind it. It's an estimate of for the next t time steps, what is the reward it achieves. So this should be an estimate of its expectation average performance from that state. So then now we can use this to basically learn some version of this and use it as one of these estimators to be able to reduce variance. So this is just reward to go is usually a very data focused way of thinking about this problem. But if you've heard or are a bit familiar with a value function or a Q function, it's basically, well, now you're learning a model for this reward to go. Where the value function is just state dependent, the Q function is state plus next action. So if the agent takes that action, it should get this much reward to go into the future in expectation. So these models then can be used as what are called critics. So it's a version of that baseline from before, but it's basically, well, now we may have an estimator for the policy's average performance that's a little bit less noisy, a little bit less variance than what is currently used from the last slide that was just using this simple baseline. And then we can basically go in and replace that baseline with definitely something like the value function. There's a couple of rules on being a bit careful about which baseline is replaced here and what you replace it with for the agent, but some estimator that basically estimates the policy's performance is almost always a good thing to replace it with. With the only caveat that so now if we're learning a model, the model is going to have some error, so some bias. So it's not going to be a perfect estimator for the policy's performance, but it's at least basically the reason that these are used is now there's some game that's kind of played where we want to reduce, in the perfect world, we want no bias and no variance, but we can't really get that. So what's the best trade-off in terms of bias versus variance? So at least when the policy ends up computing its policy gradient, it gets something that's, the most accurate as possible. So it can make a step. And I was introducing there's basically a bunch of different versions of these. I'm sure there's a couple of others as well, but these are kind of the main ones. So reinforce, which we already talked about, is just this. Use the reward to go. Works. Really high variance though. You can use something called a TD actor critic, which is just really, was this current next action slightly better? It's kind of like a one-step bit of look ahead for something that'll determine whether or not it performed better. And then the advantage and the Q function are just a bit more complicated, but they can also be used as some form of critic in this case. Okay, does that make sense? Any questions about critics so far? No? Okay, you can literally kind of think of them using that word too. Or at least some of you were familiar with critics for movies. something like that, or whatever, or plays or art. It's the idea for some reason, those people have been deemed like specialists in understanding whether or not those things are better or worse. So here, these critics, they're specialists in understanding whether or not the behavior of that particular policy is better or worse. Same process, which means that in this case, if the agent can just like ask the critic, all right, did I do better here or worse? I did better, great, I'll keep doing that again. And then, we just want some system here that's less biased than maybe like a movie critic who is maybe sometimes a little bit too artsy or something like that and doesn't represent the normal distribution of all of society. Who knows? So basically the same problems do exist. Okay. the So at least mathematically, these are not very difficult to be able to train. So if there's a value function that you want to train, one way to be able to do this is make a target. So this is just, we need some y value in order to be able to train this model. So one way to be able to do this with bootstrapping is basically for the reward the agent gets when it takes that action, plus the value at the next state, because we've got the data, that becomes the target. And then basically it'll minimize the error between this and basically r at t, let's see, plus basically v at s of t plus 1. So it's just kind of, was this reward plus the value I get in the next state better or a little bit different than what's been trained so far? Or you can roll out this and just kind of use the actual value. So that reward to go that relies directly on the data. And this won't introduce as much of the bias or really any bias because there's no trained model here, but this estimator is more variance. This estimator is more bias. So then what can kind of be done here is, okay, if one of these is more bias and one of them is more variance, is there a nice way to be able to combine these together? And this is where you can use some estimators to be able to do this for action value functions. So the Q function is just, can be expressed as if you knew what the reward was for the next state, and then the basically value from the future states. You can compute those two together and get a Q function. There are many versions of these. I'm introducing these because if you go start reading like policy gradient papers, it's kind of like up to the author's preference and how they feel like expressing the critic for their particular algorithm. So you'll see a mix of different versions of these. Sometimes you'll see advantage, sometimes you'll see the Q function. Kind of depends on preference. They're all basically connected through this formula. Like the advantage is basically Q function minus the actual value function from that particular point. Great. Still good so far? Any questions? All right, great. The all right, but this now kind of getting back to this point of being able to kind of like figure out how to reduce some of the like variance and be able to improve our estimates. So this is one way to write the variance. Because remember, we write this out and this is technically equal to the Q function here. This is correct, but it's estimating over a pretty complex distribution. So if you think about it, maybe not on a normal day, but let's say on the weekend where we probably do like less structured things and we probably do more random stuff over the weekend. But if you wanted to be able to estimate and the agent wanted to be able to estimate like its behavior and performance over that individual day, but maybe every Saturday it's experienced, I don't know, so far up to its existence in life. There's going to be a lot of variation over a lot of the things that the agent is going to do here. So it does mean that this model is trying to estimate a pretty complex distribution. Like it's doing an expectation over something that can be extremely multimodal, can have really large different values. Sometimes even like point estimates are actually a kind of poor model to be able to use here, considering like the very large and diverse and multimodal behavior that agents should have, especially to be able to find good optimal policies. So this is where basically now we can use these models to figure out like, can we estimate this advantage a little bit better? So here's kind of like a depiction of this drawing. So if an agent was at a certain point, we can maybe say like this is the Saturday morning version of this current example that's being given. There's multiple possible paths that the agent can take on any normal day like that, and they can explore lots of different states, get lots of different rewards, which means like to estimate this, the number of trajectories that might need to be like rolled out from that particular state is pretty large. But really the idea of using now this learned model is just to sum all these together and take an expectation for this. So it's trying to represent a lot of this variability over behavior that can happen into the future. Um, yeah. So this helps kind of estimate like this distribution of rollouts. Okay. So this is where, so if we're maybe using a learned model, so at some point into the future, okay, from here we can just use the model to estimate the rollouts. We can basically try to get the best of both worlds from this. So if we just do like the advantage is from what we've discussed so far, is like this single step estimate of the behavior. So it's sort of, let's say this is just one state and this is the next state, and then the model there is going to estimate the agent's performance from that second state. But this means that there's going to possibly be a lot of bias introduced from the model because it's trying to estimate over all the unique, diverse, interesting stuff that exists inside of this distribution. So some of the some bias can be introduced. So what can happen in this case is really combine these two things. So here, some amount of Monte Carlo estimates can be used across this model that's being given. So here, this is basically like take this advantage, compute the advantage for the next t steps, I guess, up into infinity. So this is actually kind of now like combining the rollouts that came from the agent rather than just using the value estimate at the next state. So now it'll introduce a little bit of variance, but this variance is true data in the world that doesn't have any bias. So at least we know that it still captures a lot of the data well, a lot of the behavior, and can end up being a slightly better estimator that provides a little bit more signal to the actual agent. Okay. Does that make sense? Any questions about that? Okay, so let me dive into maybe this diagram a bit more. So basically what happens is in a lot of the algorithms for being able to estimate basically the agent's behavior, you can use a mix of a model and what is often called n-step returns. The idea is here is, basically use some combination of the model and the data for the next n steps, rather than just doing a single step. Up here, this is basically just one step, then use the model s of t plus 1 for all future states. Here, in this case, this part is basically doing the n steps. So it'll compute the reward from like t to t prime for n up to this step. And then at t plus, n, so at some point n steps into the future, now we start using the model. So this is basically like take some rollout for a little while. That's from the actual data. And then from here, as it's kind of depicted over there, now we will use v of s of t plus n in this case for that far into the future. Maybe because often when we roll out trajectories, the further we get into the future, the less those trajectories overlap. So there's not going to be a lot of shared information up into the future and kind of not great estimate for how the behavior is going to perform. So this is also visualized over here where the agent kind of works for a little while. It's at some point. This will all be used. So this is basically the n step part. And then from, n, after n steps into the trajectory, here is where v of s of t plus n is going to start to be used at those points into the future. And then in many cases, using some value that's greater than n almost always results in a better performing policy. You can look into some more of the details in this in the RL book where they talk a lot about n-step returns. If you really want to get into the details, go check out the generalized advantage estimator paper to figure out that there's even more models that can be combined together here. Okay. Now, any questions? No? This does end up being pretty helpful too. Certainly a lot of the algorithms that are working and scaling better they tend to rely on basically being able to increase this n quite a bit, because then you definitely have a model that learns more directly from the data. Okay, we'll get into some of the details in a bit after this as well. We're going to kind of go down what I'm going to call the story of StarCraft. But basically, they also rely pretty heavily on being able to use some good n-step returns, because you need to get a good estimate for behavior for how your model works. Okay. All right. So, all right. So this is, so far, those are kind of like the main components for why, um, policy gradient methods like should be used. Basically, you need to compute some policy gradient, and the math for it is pretty well formed. If you've got some bias, some value estimator, you can basically be able to use that to get a slightly better estimate for how your policy actually works. Okay, that all sounds nice, but how does any of this work whenever we kind of pull deep learning out of our back pocket and say like, well, now I want to use this big giant model and want to be able to train this still pretty well. So don't have quite enough time to go over like all of the details for policy gradient algorithms, and certainly all the methods that are kind of like a little bit more important to get them working in practice. But I really encourage, especially if you're going to use these methods, to go check out this blog post. So this is I think this started out as like 21, and now it's up to 37 implementation details that matter like a lot for how you end up training your policy gradient algorithm. And this is a really long blog post that maybe you've got in particular questions. But part of this started was, PPO is still a bit unstable. Basically, how do we get to a point where we know it's still programmed well and works pretty well for our task? Yeah, there's definitely some details. But basically, there's a lot of questions on, so like kind of up to here, we've kind of covered policy gradients already. We're going to talk in this particular thing about a version of PPO. Basically, what was happening is there's a bunch of RL libraries. They all wrote their own version of PPO. They all performed pretty different across different tasks, different benchmarks. They ran at different speeds. They're in PyTorch. They're in JAX. I think even some of them are written in like TensorFlow, things like that. So what was actually important in order to be able to get all these to work is these many things that this person went through. So there was clearly a couple of like core implementation details. Maybe we can skip over a lot of these things and actually get to some particular graphs. But for example, I'm pretty sure there's an analysis in here between those different estimators we just talked about and how important it is to like select n properly for your n-step returns. There's also some different aspects for, so PPO can both be used for like continuous or discrete optimizations for action distributions. But sometimes, the way the continuous action distribution is modeled is important in order to get to that as well. So there's, like I was saying, there's not really enough time to cover this pretty long blog post that has a lot of details. But if you happen to be trying to program PPO and getting it to work well, some policy gradient method, and it's not working, really go and check out this blog post. It's got tons of information. This is technically a part of ICML's blog post track, so it has been reviewed by other people and other researchers as well, and they feel, confident that the information in this blog post is useful for everybody. So feel free to dig into this, especially as I think we'll get into like the last assignment for the class is a little bit about like scaling up algorithms. I'm sure a lot of the information in this blog post will help make your life easier for RL problems. Okay. Okay. All right. So then I wanted to have a little discussion about, all right, what are some of the biggest applications of PPO or policy gradient methods, but also kind of importantly, how do those even work? What were basically the tools that end up being put together to get them to function? So, okay, how many people read the AlphaStar paper yet? Although I guess the Friday is the actual deadline for reading the policy gradient papers. Okay, good. Because this is, in some ways, this is like as complicated as it gets for being able to train something that's a policy gradient. But as we've discussed, like policy gradients is still a bit noisy. So what other methods were used here in order to be able to make progress and still train a good policy? So one thing that they used is basically start out with some amount of supervised learning, because it's RL starting from complete scratch and training a policy to be optimal is extremely tricky, especially as basically more problems that are of much larger scale are explored. And in particular for this case, it's also because in something like StarCraft, like the action and state distribution the agent sees is going to change a lot. Like the agent starts out, it's basically totally random, so it's basically totally junk. So how often is it going to collect new data? It's all going to be diverse. And it's not going to be until the agent starts to get really good. But when it starts to get to that point, like the average distribution of states that the agent sees is going to change quite significantly. And this is just like a whole challenge for the entire optimization process. Like deep networks are not going to really like large changes in its input distribution over the entire learning process. We're going to have like a whole lecture on how to deal with that. And it's actually right now what people are trying to figure out in the deep RL community is as we tackle larger problems, basically how can we deal with some of the, I'll say like the challenges of the deep learning model, because it's not going to like shifting distributions a lot and like largely over the whole training process. But so then one basic, if it's possible to have access to this, then one nice way to get around this, do supervised learning first. If someone, or if for your problem, there is already some large data set that does basically prescribe a lot of pretty good behavior for the agent, then at least when reinforcement learning is applied after that, it shouldn't have to change its distribution too much. It just has to do a little bit better than what was in that data set already. Otherwise, I mean, if it doesn't work, it's probably that your data set that was gathered for this was actually not very close at all to what is optimal behavior, which makes it a bit harder to use in that case too. So there's a bit of an assumption here that RL kind of helps for this, like at the end of the process, if you really just want to like fine tune it to be like squeeze out a little bit more performance, then it works great. There's still going to be more research that's going to be needed to basically like train something like this from scratch. I spent the morning trying to find a paper for StarCraft that actually trained RL from scratch in order to be able to get to the best, and I couldn't find anything. I don't know if I missed anything, but it took a few rounds for like researchers to do that for like AlphaGo. Eventually, they were able to remove some of the like supervised learning and just train from scratch, but it doesn't seem like that's been able to be completed for StarCraft yet. Yes. Hmm. Possible, but like let's unpack that a bit. So by the simulator is too big, do you mean that like the possible number of states is too big? Or- Hmm. I mean, that definitely is part of the limitation. I don't know if that's the most complex part of the limitation. Yeah, because at least at some point, for example, I thought StarCraft would be an interesting one. At some point when they were working on this research, Google was using, I think, about 90% of its compute across the entire company in order to be able to collect data and train this policy. So I think that's a lot. I suspect anyway, I don't have like hard numbers on how that would work, but it seems like they were collecting enough data at that point. So I don't know if it's like the simulator is slow aspect to be able to run stuff. But maybe there's like a bit of a trade-off here where part of what you might have is correct, where the simulator is a bit slow, at least in terms of the vastness of the state space for this problem and how much would need to be enumerated. But I think that vastness is really what makes it a bit more challenging. Maybe if speeding up the simulator would help, but there's going to be a large change in like state distributions because Go only really had Uh, don't quote me on this. I think it's like a 19 by 19 board. So there's sort of like, 400 moves that can be made each time. But something like StarCraft, I think, has something in the order of tens of thousands of possible actions that can be made at any point in time. So the branching factor is also huge. So there's a lot to enumerate from before. So that's at least definitely part of the challenge. Yeah, other questions? Okay, stay with that for a bit, we'll keep going. So like I was saying, so they're using a version of TD-Lambda. This is very similar to doing n-step returns, but then Lambda kind of dictates like how many steps into the future. It averages trajectories from itself. This is its model it's trained. It uses V-trace. So we talked about a bit in the last class being able to do importance sampling so that the model could still use a bit of the data, even if it's from an older version of the policy. So this was also trained in a somewhat complex distributed RL training process. So the data is usually a bit behind what the current policy is being trained like for right now and shipped back. So this V-trace helps the model at least be able to train correctly over some amount of slightly off policy data. It's not really, really off policy. It's sort of like off policy within a few seconds, which means that there's probably only like 20 to 100 updates that the learning model has received that's different from the data that's received from the actual data collection process. Okay, so we haven't covered a lot of distributed reinforcement learning. We did in like one slide, but the idea is there's one thread taking data from a bunch of different agents that are out collecting data in all the StarCraft environments. And then that thread is making some updates on the model, and then it's sending those models back to those different threads that are collecting data. So there's going to be some difference between the learning model that's the most up to date, and then the models out there collecting data are going to be sending data back from slightly older versions of the model. So then this helps the learning agent still be able to like make use of the data from the slightly out of date policies that are collecting data. Amongst other things. And they used a version of UpGo for better advantage estimation. I forget some of the details on that, but obviously being able to get that estimator right was important. Okay, so any other questions about AlphaStar? All right, so nice part is, all right, there's still some ways to be able to reduce this. So this, like I was saying, required a pretty significant amount of computes to be able to train this agent. This was at least some newer work that was able to like scale down the amount of compute and overall learning that was needed. So this was one thing that could be done is reducing the input size. So here, the entire observation for what the agent sees of the map, it could reduce the resolution of the image because it wasn't all needed. Yeah, this is always a kind of tricky question, but it was also possible to reduce the amount of behavior cloning data. In that paper, they were mostly saying that so a lot of the data in the data set was actually really similar to a lot of the other data. So it was possible to go into this, basically kind of like check similarity across some of the data, eliminate a large amount of it such that only like unique and good data is kept. So then you didn't have to have, as many GPUs to store like the replay buffer or the BC data in order to be able to train it. So this is actually always a good process. If some behavior cloning is going to be done, I mean, use the best data, but you can often remove stuff if it's just a repeat of other data, which happens a lot in behavior cloning in RL. Typically, the agent generates a lot of stuff that looks pretty similar because of the way it explores. And then for a balance here, it's always important to get like exploration diversity right, especially after doing behavior cloning. Okay, so the positive part about using behavior cloning, it saves the agent a lot of time for being able to train itself to get up to that point, often helps with optimization. The negative part is it can often like really shrink the diversity of behaviors that are going to come out of the policy. So at that point, what they've also worked on here is like, okay, well, adding a little bit more diversity and encouraging the policy to explore a little bit more broadly outside of that like data set from behavior cloning that's collected already. And that'll give it some better chances to find some like more optimal trajectories, which will lead to more optimal policies. So just be a bit careful with the way these two kind of mingle with each other. This also happens a lot for people that are fine-tuning language models these days, because the RL HF process is normally, okay, do some RL, but then there's a pretty heavy constraint on like keeping the distribution similar to the old model and not deviating from that much. But here, at least in this case for StarCraft, there's probably like less of a constraint on that. Like, don't get too far away from the old model. That seems to be really good, and more to like explore stuff, maximize your reward, be more diverse, at least for this type of problem. Okay, does that make sense? So this is a little bit of a story. So sort of first step, throw a whole bunch of compute at this problem, use RL, use a good estimate for the advantages, and then you can finally develop a pretty good policy. And then with a little bit more practice and time, you can like reduce the amount of data required that's needed. And then the last step that seems to go for this is actually being able to do this from totally offline data, because behavior cloning might have some challenges. One thing is that, you know, you need to always have expert data in there, but if you can at least do something like offline learning, which we'll talk about a little bit more, means that you can use all data. It doesn't always have to just be expert data. And if your RL offline algorithm is programmed really well, it can figure out how to even kind of connect together some policies and trajectories where maybe like part of this segment of an expert's trajectory is great, and then part of this other segment from a different expert's trajectory is even better. So it can figure out how to connect these together and get even better performance. But now this is sort of like before it had to do these two steps, like do supervised learning, then do RL. And now in some ways doing offline RL is kind of combining these two together and still doing it in a more stable sense because the data distribution is not going to change. So it's also making it a bit easier to kind of train these models and not have so many like artifact generation steps where like, well, now we do supervised learning, now we do RL, now we have to do supervised learning again, and then RL. If you think about it, this also becomes like a really hard thing to manage in terms of like science. Now there's a whole bunch of steps. You can make more mistakes in here all the time. It's maybe not always so clear like what is delivered at the end of each of these steps. So if we can make just one algorithm that handles most of like the problematic cases, and offline RL was a pretty good example here, then this ends up most often working a bit better. Maybe you've kind of run into some of this stuff in your life, probably. If you ever have to do something that's many complicated steps built on top of each other, and you make one mistake, you got to start from the beginning, like all over again. But if it's easy to just make incremental improvements in this more monolithic training process, it's sometimes easier to dump data into it and just let it compute. Okay. All right. Does that make sense? All right. Good. We'll see. At least, yeah, didn't find any papers yet that were doing this. Yeah, totally just like running RL without any sort of behavior cloning. So it still seems to be some amount of, I'll call it like necessary step for some of the larger applications of policy gradients. All right. I just wanted to kind of talk about two other examples here. So one is there was the other paper that was assigned, and this is kind of OpenAI's Rubik's Cube. So this is basically, I should include a picture of it, but this is a robot hand that's basically figuring out how to organize and like rotate a Rubik's Cube. And this ends up being kind of complex in order to be able to train, but the goal of this particular design is to be able to basically use a lot of sim to real training. So there's a simulation of being able to like rotate this Rubik's Cube around for this hand, and then it can do a lot of simulation in order to be able to understand like how to actually reach these goals for rotating this Rubik's Cube and solving it. And then eventually this is applied to the real world and hopefully transfer happens. But we'll go over like a whole class on sim to real training as well and how to scale that. But the real idea is what was helpful here. One is, okay, I know this is from like ancient time ago, so they were using an LSTM instead of a transformer. But part of what was implicitly learned inside of the LSTM is it's kind of performing like a version of like meta learning and system identification. So in this case, In the simulator, basically like the physics were randomized, the weight of the cube was randomized, and then hopefully what happens is the agent then learns to just quickly figure out what all these parameters are as it starts operating. And then it effectively knows like what the dynamics of the objects are so it can perform well on its task. So this can just be kind of like implicitly just the LSTM will take care of that. And then when it was deployed on the real world, it could in the first like half a second basically figure out what those parameters are, and then it can get to work on actually solving the task. So it's a nice way to do this implicitly. There was one other interesting thing that's done for I'll call it sim to real case, but in the simulation, it's possible to have access to some extra information that's not going to be available in the real world, but it often helps basically get a more accurate value function. So you get a better estimate of how to be able to train the policy and its behavior. But then in the real world, basically all that is needed is the policy to actually be able to just use it. So the agent isn't learning in the real world, it's just running out its policy. So in that case, it no longer needs, well, it's possible to train this in such a way that the value function gets access to what's called like uh, extra information, or basically like Oracle information that it's not going to have, but it does just help the algorithm learn. And then it learns, it just gets this better policy. It's kind of like the artifact that comes out of this, and then you can just use that in the real world. So this is at least like another version of this lesson of like use whatever you can in order to be able to get a better estimate for your policy gradient. And because in the end, all you really need, or all the agent really needs, is the network architecture for the policy. So all this stuff is inputs only available in simulation, and these are actually available in the real robot. So there's basically some dividing line where none of this stuff goes that way at all. Okay. Does that make sense? Good. Yeah. Hmm. Yeah, in this case, this has more to do with just like the uncertainty over the dynamics of the actual task. So although, well, like actually for the Rubik's Cube task, there is quite a number of actions because it's this kind of complex hand that I think has about 26 dimensions to it for being able to control all the joints, which is actually quite a bit for a particular robotics problem. So there'll still be some variance over the possible trajectories. And just remember the variance over those trajectories can happen both from having like a high action space, a high dimensional action space. So there'll be many possible trajectories, and just like any stochasticity in the dynamics, because both of those affect the actual like distribution of trajectories from the policy. Yeah, so this is where, but that's also why for this project, yeah, they also collected a huge number of trajectories for every policy update. So they're still trying to handle the amount of variance that actually comes from each update kind of carefully. So I think both of this paper and certainly like the AlphaStar and StarCraft papers are collecting really a quite large number of trajectories for any policy estimate and update. Okay. Uh, yes.
When we talk about not sure like extra information that we never had in the real world, or we just have the information, but it is one of the problems
Hmm.
cover up. I'm guessing that they
Mhm. Mhm. It's a bit of both, but more so in this case, it's like extra data. So like true ground truth information is what they mostly mean. So for the policy, at least in, sorry, for the value function and simulation, um, Like it will be given the current parameters that describe like the physics and friction and color of the cube and size of the cube. But then in the policy and in the real world, it doesn't exactly have like the configuration of like the Rubik's Cube and an exact measure for the physics or the friction that goes on in the real world. So usually what happens is there's going to be some amount of, I'll call them like omega parameters. These are things that are part of what actually describe the dynamics, like so the physics that goes on in the world. So these will be hidden from the policy, but given to the value function here. So you basically have, think of it as like extra sensors that you don't really, the robot won't have access to. In this case, these are like perfect Oracle sensors, so they never really exist in the real world. Yeah. I mean, you can almost, I don't think having training wheels is a good analogy here, but somehow if you knew more about the dynamics of the world when you first start to learn to use a bike or something like that, it probably helps. But then at some point you don't need them anymore. It just becomes a little bit more common nature. You've like figured out how the problem works. Good, you've got a good estimate for it. You don't need to track the dynamics quite as much. It's maybe kind of one way to think about it. Okay, other questions? All right. So then this gets to one of the newer pieces of work. Where now this is also like figuring out how to scale up RL really well, especially when we get into more diverse environments. This one's also nice because it was used on robotics tasks more. But there's a nice, a recent paper called Polyformer. Okay, short story leading into this. There are very few papers that have been able to train like an RL policy with a transformer as part of the network and being able to do this from scratch. And well, technically this still isn't entirely from scratch, but there is still quite a bit of a challenge figuring out how to basically like combine policy gradients and transformers, have them play nice with each other, be able to start from scratch and train a good policy. So there's only maybe 2 or 3 papers I know of that have managed to do this on kind of more specific problems. It's not a general easy thing to do. Like if you go look at RL libraries, very few of them are going to have transformers as an option for your policy network either, just as a hint towards this. But this paper was a bit of an exception where it's trying to figure out, okay, how can this be scaled a bit better? And there's a little variation basically on the story that we've talked about so far. So this is still basically the same recipe for having a lot of parallel rollouts. The transformer policy is going to be using some vision transformer already that kind of controls the inputs, which you'll get a bit more familiar with homework 2. Something that's going to take the goal as input and encode that as well. And then this is the part that's like doing the encoding, and here's the actual transformer that needs to be like trained. And the idea is transformers are pretty good at handling like large diverse data, so it should be able to scale well if we can somehow manage to deal with the like complexities of the optimization and the training. Okay, so this ended up kind of combining 2 things, so it didn't kind of like necessarily use behavior cloning like some of the previous papers have to start from. One thing that it did use though is it started out with basically like a pre-trained vision model. It used Dino V2. So it's not necessarily starting entirely from scratch, but this is almost like saying, okay, we're going to start RL from sort of scratch, but let's at least say, okay, like our perception model is good. We don't need to, our RL training process does not also need to figure out how to perceive how the world is going on. It's going to start out with a pretty good understanding about how to pick up, like not pick up objects, but understand objects and figure out the scene. So this does at least provide, an extra step up when going to train this actual process. And then, yeah, it's kind of important, but probably a little less important for this current discussion. Yeah, some other like FLAN T5 model for being able to encode the text. But I don't think the text is where scaling was more challenging for this model. So then from this, using this particular model, so it's basically got perception solved already. Then from here, it basically now start to train this transformer in order to be able to figure out the RL problem. So this is like the decision-making problem for which actions to take, given how the world is currently perceived. So here, this is a different way to be able to kind of break up the challenge in this optimization. So at least gets over that first somewhat large like hurdle of figuring out how to perceive the world entirely from scratch. And there's a couple of other interesting bits about how the algorithm works. They also use the input is actually quite a large history of a lot of the previous states, so it can figure out where it is in its current plan. So they use a kind of interesting way in order to be able to cache a lot of the information in the transformer. So it doesn't always have to feed like, here's 50 states again and to compute everything through the transformer again, which would be really slow. So it can cache basically the 49 steps from the previous frame and to just introduce the new one. So it's saving a lot of compute. And if you're interested, yeah, you can go read into the distributed PPO paper to understand more about how it's actually doing the optimization over a whole bunch of parallel threads operating at once. Okay. Any questions for this one? Is that a question or stretching? No problem. So this is like there's a lot of good information inside of this paper for figuring out how to scale up deep RL algorithms a bit more. And it's not quite as complex or require as much compute as the like StarCraft papers do as well. And this one is, well, kind of done by an academic institution instead of a giant industry one. So I forget, I think there's some code actually released for this one as well. Can be used. Okay, any questions? What are we doing? All right. There is still a bit of this discussion that I wanted to have, though. It's kind of like, all right, how do we summarize and connect all this together? What are the, at least like things to start with if the plan is to try and use RL at some amount of scale for some kind of robotics problem? In this case, what was done in this paper is doing some amount of navigation. Then here, maybe one question to even start with is kind of like, where do we start with RL? So like in the StarCraft paper, there's a whole bunch of basically behavior cloning used first, and then RL is used. In the last paper, it was, okay, to some extent, the perception problem is like solved first, and then RL is done on top of that. So it's to think about and have a bit of this discussion. There's at least there's like a bare minimum that sometimes needs to be done, so RL can work. But then there's also like a more theoretical discussion of like which parts of these problems do we actually want to use RL for? So maybe I'll start this discussion with this question of maybe we'll even do a show of hands for see who's thought about this a bit for. So if we're going to do reinforcement learning, should we be using reinforcement learning to also solve the perception problem? Or do we think it's better to pre-train some model for perception? So like, who thinks it's better to pre-train some model for perception? Yeah, got some computer vision people in here, some structure. Okay. All right, so then who wants to totally learn like perception and everything from scratch using RL? Who's the believer in the totally end-to-end process for training? Nobody in here? Oh, interesting. Okay. Okay, but then all right, so if we're starting for some perception stack, then do we notice none of these papers did anything like introduced some perception model and then did behavior cloning on top of that for some reason. So any ideas why that wasn't so necessary? Yeah, so that's good question. So like well, like one way, at least so this is a bit easier for everyone to understand is like you could take a model that's been trained on like all of ImageNet. So at least it's learned to perceive, like the 1,000 objects. that are inside that actual data set. So it's got some good structure for identifying like background, foreground images. So then this isn't something that'll be needed to learn from scratch from the RL policy. So there's something about this. And like this premise is what a lot of like the entire computer vision community is kind of built on. There's going to be some useful perception representation that can then, at least in my opinion, that can then be used for the planning that's done next, whether or not it's like for self-driving cars, whatever. Yeah. Yeah. Hmm. Well, like in practice, definitely. I suspect maybe in like the previous paper, it was just they didn't have that data collected yet, potentially. Although that's sometimes just research papers are sometimes weird things where it's just sort of for the research purpose, they skipped that step because they didn't want to add in more assumptions maybe into their method occasionally. Hmm. Um, yeah, other ideas?
They also have take the word, take the word. So
Mm.
feel like enough points. The problem like StarCraft is still more like it is a maybe be able to put in points the words to get um kind of ignorance.
Hmm. Yeah, because I think even for like the StarCraft paper, the agent gets a reward of 1 if it wins. I believe there are no dense rewards in that environment at all, and it could take up to, I'm not a StarCraft expert, but like I guess 20 minutes to an hour to actually win a game. So that's one bit of information on how the agent performs after 20 minutes to an hour, like 20 to 60 minutes. So, okay. So you think, yeah, maybe behavior cloning isn't needed if you have a fast simulator with a, I'll call it like a perfect dense reward function. Maybe perfect is a bit strong. Hmm. Hmm. Okay. Good. And then maybe just like last question to kind of think about this too is also to think about like a whole first part of the class was doing behavior cloning quite a bit. And at least for some of these like large models that are being used for just like behavior cloning for robotics, not many of them use a lot of like pre-trained models for perception. And there's not a lot of robotics data yet. So there's maybe something more that can definitely be done in this area at some point, like figuring out how to, um, like in the real world, we don't have a fast simulator or a great reward function. We're going to probably have to collect some data, maybe some data for RL, but in order to reduce the amount of data that might need to be collected for like even these large models, some amount of these pre-trained models are likely going to be helpful. I'm not saying it's going to be easy to figure out how to glue them all together and get this to work, but something about this should help. Like at least in this RL paper, it seems to work well when they start from using Dino V2 to cover perception. Otherwise, they'd probably need a lot more data at the very least in order to be able to train that model. So we're kind of in a bit of a stage of figuring out how to explore combining these models, which ones are good and bad, which ones actually save on having to collect more data for robotics problems, which ones don't. And at least we should kind of think about the interplay between these things when we kind of like pick models or think about really like wishes. If I wish this model existed, and then that would solve a lot of problems for me here. So maybe if there was one totally general perception model, then we could still like plug that into the bigger models we're making, but we still need to figure out planning. Like planning is not easy. Planning and figuring out perception is even harder. So how can we try to make this easier for ourselves? Okay, let's take a break. Where are we? Yeah, and we'll start again at 2:37. Oh. Hmm. Oh.